All right, in today's lesson, we're going to learn how chemists can actually do experiments to figure out what the empirical formula is for a specific compound that they're working with. Most of the time, or a lot of the time, the way they do that is by doing a combustion analysis. And if you recall, combustion just simply means that you're going to burn it. And hopefully you also recall that anytime you burn something, you're going to require oxygen. So oxygen is going to be something that we're going to be utilizing a lot here in our analysis of these particular compounds. We're going to start with the most simple type of analysis to do, and that's if you take a metal and you burn it in oxygen. A lot of the metals, when they burn, you may not initially think that a metal can burn, but if you use enough heat, they will burn and you will form a metal oxide out of them. In fact, I've included a couple of videos with today's lesson where you can actually see some metals burning. If I had you in a physical classroom with me, I'd pull some samples out of my cabinet and I'd set them on fire so you could actually see them, but since we can't do that, video is going to be the next best thing. So a lot of the metals that you're going to see, and you saw a little bit of this, these metals burning when we talked about spectroscopy earlier in the year. But these metals, when they burn, often give off a whole lot of energy, and so the results are really, really bright lights that happens when these things burn. You can also do this very same type of problem I'm going to show you today. You can do that same type of analysis if you take a gas and burn it, and on one of the review problems that you're going to be doing a little bit later on, they have you, I think it's nitrogen, I think they say they burn nitrogen. And when you do that, then they will be able to, you'll do the problem the same way as when we're doing these metal oxides. Okay, so let's look at the problem that I gave you for video number 4. The problem says when 4.01 grams of mercury is strongly heated in air, the resulting oxide weighs 4.65 grams. And we're going to calculate the empirical formula of the oxide. Now, the assumption that you're making here is that because we're making an oxide, we're only working on with two specific elements we're going to be working with, in this case mercury, and we're going to assume that it's combined with oxygen and that those are the only two things that are going to be involved in our final compound. So, as is very typical, if we have a mass in grams, the first thing we need to do is convert that to moles. So, if I have 4.01 grams of mercury, and the symbol for mercury is Hg. I'm going to put that over 1, and if you look at the periodic table, you'll find that the molar mass for mercury is 200.59, whoops, not 5G, 200.59 grams of mercury for every 1 mole of mercury. So my grams will cancel out. You can see that this molar mass is very, very heavy, and I don't know if you've ever had an opportunity to see mercury. Mercury is actually very toxic. When I was in high school, we didn't realize how toxic it was at this point, and we actually would have these little balls of mercury and we'd roll them around on the table and play with them, and now we realize that really wasn't such a smart thing to do. But it is, if you have like a quart jar and you have just maybe even this much mercury in it, that jar is really, really heavy. So it doesn't take a lot of mercury to have a whole lot of mass. Okay, so after I get off that rabbit trail now, once I turn my grams of mercury into moles of mercury, this comes out to be 0.0200 moles of mercury. Now, an empirical formula is the simplest ratio between the number of atoms, and the number of atoms is directly related to the number of moles. So if I know moles of mercury and I know that it's combined with oxygen and I find moles of oxygen, then I'm going to be able to figure out the ratio between the two. Well, it says that my final resulting oxide is 4.65 grams. So if 4.65 grams is what it ends up as, and 4.01 grams of that was mercury, that means the rest of it has to be oxygen. So that means that I have 0.64 grams of oxygen in my compound. So now that I know the mass of the oxygen, I can take the mass of the oxygen and I can convert that into moles of oxygen. Okay. One other note here too, we talked about how oxygen is diatomic, but it's only diatomic if it's by itself. When it's combined with another atom, it's not diatomic, so I want to know just moles of oxygen atoms, and I don't have to worry about anything being diatomic here, so don't let that confuse you. Okay, so 1 mole from the periodic table is 16 grams, so grams will cancel out, and 64 divided by 16 is 4, so this is going to give me 0.04, actually one more significant figure, moles of oxygen. Okay, now, we're going to see this technique used throughout a whole lot of the rest of the problems in the rest of the chapter, okay? I have this many moles of mercury, and I have this many moles of oxygen. I want the simplest whole number ratio, so the easiest thing to do is going to be to take the smallest number that I have and divide that through all of my moles. So 0.02 is smaller than 0.04, so what I'm going to do is I'm going to divide this by 0.0200. I'm going to divide this one by 0.0200. And when I do that, that will give me the simplest whole number ratio. So when you divide this, 0.02 divided by 0.02 is 1. 0.04 divided by 0.02 is 2. And what that tells me is that for every 1 mole of mercury, I have 2 moles of oxygen. So that's going to be HgO2 for my empirical formula.